This topic is about organic chemistry. Probably you have heard about organic foods, organic farming. So they borrow this term from what we call organic compounds. And the chemistry that we are going to look at is the study of those types of compounds. So some examples of organic compounds that we usually use in nature are fats. Uh, Probably you have heard some people saying, oh, there are bad fat and good fat, especially when you talk about heart disease, cardiovascular disease, when we talk about cholesterol. So fats are a type of organic compounds, and these are the formulas of the fats. And you can see that they have a lot of carbons. They have what we call carbon chains. Now, if we give a three-dimensional model of fats, we have three types of them. We have trans fat, which is the most dangerous. So I say the most dangerous. We have unsaturated fat, which is also called cis fat, but we'll talk more about this. This one is beneficial. This one is usually beneficial fat. Then we have saturated fats, which is second most dangerous. Yeah, it also has some benefits, but we are going to focus on fats later on. Now, what is this organic chemistry? Organic chemistry studies compounds containing carbon as their backbone. So here I'll remove this and say, and the reactions these compounds undertake. So, and the reactions these compounds undertake. So, throughout this topic and chapters related to organic chemistry, we are going to be looking at two types of organic compounds. The first type is hydrocarbon. We call them hydrocarbons. You will know why we give them that name. The second group of organic compounds contain heteroatoms. So I'll just write down some structures here. Like if you have CH3, you have a hydrocarbon. If you have CH3, CH2OH, you have an organic compound containing heteroatom. So this is organic compound containing heteroatom. In this case, our heteroatom is oxygen. So what it means, on an organic compound, a heteroatom is an atom other than carbon and hydrogen. That's what it means. So here we see that we have only carbon and hydrogen. Here we have an atom other than carbon and oxygen. Now another question is, Where did the name organic come from? So the origin of the name organic means only produced in nature, not in the lab. So only produced in nature, not in the lab. That's what organic means. This came about because initially people thought that organic compounds are produced only in nature. You cannot synthesize them in the lab. But we later realized that it is not true. So we can say that organic compounds are actually produced in nature. That's what we know. This is true. But we also have some organic compounds that we can synthesize in the lab. So this is where the name came from. But now we know that we can synthesize these compounds in the lab. So we are sure about that. So we still maintained the name organic, although we discovered that we could synthesize them in the lab because the name already stuck. So these are what we call organic compounds. Then we have inorganic compounds. I think up to now, those are the types of compounds that we have been studying. These compounds or this type of chemistry studies compounds whose backbone is not carbon. So like ionic compounds, ionic ionic compounds, common acids, and bases are mainly inorganic acids or inorganic bases. So these compounds do not have a backbone of carbon. So examples are like NaCl, HCl, H3PO4. All these are inorganic compounds. Now let's look at some organic compounds that come from natural sources, from plants and animals, especially pharmaceuticals. Here I'm just giving you two pharmaceuticals, two drugs that come from plants. Quinine. So quinine is an anti-malaria drug. Actually, I have used it for some time. And we have morphine, which is an analgesic. Now, these are the structures. This is the structure of quinine. This is the structure of morphine. All these corners you see here contain carbon. So carbon is the backbone of this molecule. The same thing, all these corners you see on this molecule means we have a carbon there. So carbon is a backbone of this other molecule. That's why these molecules are known as organic compounds. But they come from plants. So they have natural sources as their origin. We also have some pharmaceuticals, some drugs that come from animals, like some cholesterol drugs come from animals. But we are not going to talk much about those. Now let's look at hydrocarbons. What are hydrocarbons? So by definition, hydrocarbons are organic molecules that contain carbon and hydrogen only. That's where the name comes from. Hydrocarbon, carbon and hydrogen only. One of the most famous hydrocarbons is gasoline. We use gasoline in our cars, and that is an example of hydrocarbon, especially octane. Um, Octane hydrocarbon is the one that we use in gasoline. Now here we have three types of hydrocarbons. We have the alkanes, we have the alkenes, and then we have the alkynes. So alkanes have single bonds everywhere. Alkenes have one or more double bonds. Alkynes have one or more triple bonds. That is the difference between alkanes, alkenes, and alkynes. Now, these ones, because they have one or more double bond, are known as unsaturated hydrocarbon. The same thing, this one is unsaturated hydrocarbon. This one has single bonds everywhere. It is saturated hydrocarbon. What does saturated mean? It means we cannot add any more hydrogen atoms. So a saturated alkane or a saturated hydrocarbon means you cannot add any more hydrogen atoms because we have a single bond everywhere. Now, the unsaturated alkanes, the unsaturated hydrocarbons means you can add more hydrogen atoms on the double or triple bond. So what it means is I can decide that I want to add hydrogen here. I can add hydrogen, which means I have hydrogen here, and then this bond breaks to form this molecule. I can add hydrogen here, this bond breaks to form that molecule. So if you can add more hydrogen to the molecule, that molecule is unsaturated. Now, if you cannot add any more hydrogen, that molecule is a saturated hydrocarbon. So on this same slide, let's look at another concept. Now, if you look at the alkane, if you look at this alkane and just take this carbon, there are 4 groups of electrons surrounding this carbon. So this is one group of electrons, one group of electrons, one group of electrons, one group of electrons. So what it means is that this carbon, a carbon in alkanes has a tetrahedral electron geometry. bond angle 109.5. That's what it means. Now, if we go to alkenes, if we go to this alkene, we have one group of electrons here, the second group of electrons, the third group of electrons. So the carbon that has a double bond has 3 groups of electrons surrounding the central atom. So we can say the carbon with double bond has trigonal planar electron geometry because it has 3 groups surrounding the central atom. The same thing with this second carbon. 1, 2, 3. So the bond angle there is 120 degrees because it's a trigonal planar, and the trigonal planar have a bond angle of 120 degrees. For the alkynes, the carbon with triple bond has a linear electron geometry with a bond angle of 180 degrees. What is the reason for that? This carbon here is surrounded by 2 groups of electrons, this group and this group. The same thing with this carbon, surrounded by 2 groups of electrons, this group and this group. So the carbon with the triple bond has a linear electron geometry. Now, if we look at these 3 molecules, what does this mean? So I'll get rid of so I want to put the bond I want to put the geometry of some of the carbons in here. So this carbon and this carbon, both of them are tetrahedral. This carbon and this carbon are trigonal planar. This carbon and this carbon are linear. This carbon is a tetrahedral. This carbon here is also a tetrahedral. So even within an alkene or an alkyne, there are also tetrahedral, except where we have a double bond and a triple bond. This carbon here, this carbon here, and this carbon here, all of them are tetrahedral. So we need to take note of that. It's only these 2 that are linear and these 2 that are trigonal planar. Now let's look at this hydrocarbon that we call alkane. I am going to start with the formula of alkanes. Now, the molecular formula of alkane is given as CnH2n plus 2. So N is number of atoms. So an example, if an atom has 5 carbon, if a molecule or if an alkane has 5 carbon atoms, so an alkane with 5 carbon atoms, if we use that formula, we are going to have C5, then H5, not 5, H2, then H 2 times 5, so I'll put this in parentheses, then plus 2, which is C5H12. So if your alkane has 5 carbon atoms, it is going to have a formula C5H12. So let's count. This one has 1, 2, 3, 4, 5 carbon atoms. How many H atoms does it have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it has 12 hydrogen atoms. Let's look at the second alkane here. How many carbon atoms does it have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So it has 9 carbon atoms. So the formula will be C9. Then H, parentheses 2 times 9 plus 2, which gives us C9H20. So this is the formula of alkane, given as CnH2n plus 2. Now, when we talk about alkanes, we have what we call straight chain alkanes. So they are just written as a straight chain, as you can see this one. They don't have branches. Then we have branched alkanes. Branched alkanes have junctions. So this is a junction. And this is another junction. So branched alkanes have junctions. So junctions are different from corners. I can have an alkane like this one, say C H H H H H here, C H H. Let me maybe get rid of this. And take a corner here and have C H H and then C H H H. This one is a straight. This one is straight chain because it does not have a junction. It has only a corner, not a junction. So we need to differentiate between a corner or a bend and a junction. A junction, you need to have a straight line, and then another atom connecting to that. That's what a junction is. While a corner, you just bend. I can just bend this one to make it look like this. It is still a straight chain, but just made a corner. So it doesn't have a junction. But a junction is like you have this, and then you have a junction here. This is a bend. This is just a bend. This is a junction. So straight chain alkanes can have bends, but branched chain alkanes have junctions. So let me just get rid of this again. And so this one, the alkane that we have here as a straight chain can actually be written as C, 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 C. 1, 2, 3, 4, or another C here. So you can see that it has these bends, but it is still a straight chain. So although it has bends, it is still a straight chain alkane. Now the one that is here that we have, this one can be written as C, 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 C. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then we have a junction here, C, C. And then we have another junction here, a wrong junction. So we have another junction here, C. So these ones are junctions. That's the difference between a straight chain and a branched chain alkanes. Now I will just quickly talk about the physical properties of hydrocarbons, especially alkanes in this case. Now here you have 3 molecules. Let me call them A, B, and C. So the first ones are straight chain. So this and this are straight chain. This one is branched. Now, if you are dealing with straight chain alkanes, this molecule is small, this molecule is big or long. It has a longer chain. Now, if you are dealing with straight chain alkanes, the bigger the molecule, the higher the boiling point. So that is one point that we need to make. Let me just say one thing. So for straight chain alkanes, that is property 1. For straight chain alkanes, the bigger the molecule, the higher the boiling point. So the bigger the molecule, the higher the boiling point. You can see this molecule has 5 carbon. 1, 2, 3, 4, 5. This one has 5 carbon. and this one has 1, 2, 3, 4, 5, 6, 7. This one has 7 carbon. So the bigger the molecule, the higher the boiling point. So we need to take note of that. In an exam, I can just give you molecules with different numbers of carbon atoms. Your job is to determine that this one has higher boiling point than this. So that is for straight chain alkanes. Now, if you have a straight chain and a branched alkane, so for the same number of, so this is property 2, for the same number of carbon atoms, straight chain alkane has higher boiling point than branched alkane. So for the same number of carbon atoms, straight chain alkane has higher boiling point than branched alkane. So if you look at, if this is A, B, and C, B has 7 carbon atoms. So this one has 7 carbon atoms. C also has 7 carbon atoms. But you see the boiling point of C is less than the boiling point of B, because C is branched and B is straight chain. So that's another property of hydrocarbons. The branched ones have lower boiling point than straight chain ones. Other properties of hydrocarbons is that they are non-polar, so they do not have polar sides. They do not have polar sides, which means because they are non-polar, they are not going to dissolve in water. So do not dissolve in water. But they are going to dissolve in organic solvents. So they dissolve in organic solvents. So they can dissolve in some nonpolar solvents. And because they are nonpolar, they are usually used as organic solvents. Usually, we use hexane as an organic solvent, a solvent that dissolves nonpolar molecule. So this is usually a solvent that dissolves other non-polar molecules. So these are some of the properties of alkanes. We talk about their boiling points with size and branching, and we talk about their polarity. We talk about their dissolution and their use as organic solvents. Actually, another property, a very important property of these alkanes is that they burn in oxygen to produce energy. So alkanes, another property is that they burn in oxygen to produce energy. That's how we get energy from gasoline, because of that property of alkanes. They will react with oxygen to produce energy, and we use that energy to power our vehicles. The same thing, energy from natural gas. That's another example of alkanes. We use natural gas to heat our houses. That energy is their property to burn in oxygen. Propane lamps are using the same property, burning in oxygen to produce energy. How do we name alkanes, especially straight chain alkanes? So we name them based on how many carbon atoms they have. So naming is based on the number of carbon atoms. So they have what we call a prefix and an end. So all the alkanes end with the name N at the end, ANE. If an alkane has one carbon, we call it methane. So if you have CH4, that is methane. If an alkane has two carbon atoms, you call it ethane. So you have CH3, CH3, which is ethane. If an alkane has three carbon atoms, you call it propane. So CH3, CH2, CH3, propane. So starting with four carbons is butane, CH3, CH2, CH2, CH3. That is butane. Then we have pentane, hexane, octane, nonane, and decane. So decane has 10 carbon atoms. So you have to go back to your book and look at all those names. So what I can do is I can give you something like this. Let's say I have an alkane, CH3, CH2, 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 CH3, and ask you to name this. So you look at the alkane like that. You say, how many carbon atoms does it have? It has 7 carbon atoms. So something with 7 carbon atoms is heptane. So that's that's how we name alkanes. We start with the prefix and then end with N. So get to know these names of alkanes. Now, When dealing with organic compounds, normally we use their structure. So we call it chemical structure or structural formula. And we have actually three types of structural formulas or for alkanes. The first one is this stick and symbol structure. This one is known as Lewis structure. So you can see it is like expanded structure. So you have to draw the sticks and the symbols. But if we don't want to use a lot of space, we use condensed structure. So these are the condensed structure. So we have C here. In the Lewis structure, we have C, we have H, H, H. So we have H here, H here, H here. So this becomes CH3. Then we have C here, then H, H. This becomes CH2. The same thing C here, then H, H. This becomes CH2, CH2, CH3. So these ones are condensed structures. So if you want to conserve space, you are going to use condensed structures. Now let's look at this. We can see the junction here going all the way, having this structure. And this is how we draw a junction for condensed structure. We put a junction here and then CH3. Actually, this one can also be written as CH3 so this one can also be written as CH3, CH2, and then a junction here, CH3, let me just get rid of one of these. A junction CH, then CH, CH3, or I mean CH2, CH3. So let me also talk about something that we need to take note of. Now, if you are dealing with an organic or if a hydrocarbon, you need to know that each carbon has 4 chemical bonds. So each carbon has 4 chemical bonds. So if we reach a junction, like let's say this junction, so we are coming from H3C, we go to that junction, C, then we go another CH3 down here. If you go here, you can see that we have CH3 here, CH3 here, and we have an H here, which means this H is also a chemical bond. Here, we put it here. And then go on to another CH. So we have a chemical bond here, the second chemical bond here. This CH is a third chemical bond, although we don't show it. So there is another chemical bond here on this junction. And then we have a fourth chemical bond that is connecting this carbon to the other carbon. So we have one chemical bond connecting the carbon to hydrogen, and we have another chemical bond connecting carbon to carbon. So at this junction, we have actually 4 chemical bonds. So we need to take note of that. Each carbon must have a maximum of 4 chemical bonds. And in condensed structure, we need to know that there is a chemical bond between carbon and carbon. There is another chemical bond between carbon and hydrogen. So here, this one, this chemical bond here is this. This chemical bond here is this. This chemical bond here is these two. Then this chemical bond here is this from here to here. So each junction has 4 chemical bonds. Now, normally when you have a junction, normally without a junction, you have CH2. When you add one junction, it means you remove one hydrogen atom. That's why we have only CH here. The same thing, we have added a junction here, we remove one hydrogen atom because that hydrogen atom has been replaced by the junction. That's why we have CH here, CH here, but we have CH2 here. The end carbon has 3 hydrogen atoms, like you can see here, CH3, CH3. So the carbons at the end have 3 hydrogen atoms, so that in the end they form 4 chemical bonds. The carbons in between have a maximum of 2 hydrogen atoms. If you add a junction, the carbon will have only 1 hydrogen atom. If you add two junctions to that carbon, the carbon will not have a hydrogen atom at all. So we can have CH3, C, CH3, CH3, then CH2, CH3. So you see that this carbon has no hydrogen atom because the hydrogen atoms have been replaced by the junction. So let's take note of that. So this is Lewis structure, this is condensed structure. Now if I get rid of this, instead of condensed structure here, I say skeletal structures. So skeletal structures, they take the Lewis structure and remove all the hydrogens. Not remove, but we don't show all the hydrogens, and we don't show the carbons as they are. We just put lines instead of that. So what we are saying is, from this Lewis structure, this part here is this carbon we see here. This second carbon is given by this corner. The third carbon here is given by this corner. The fourth carbon here is given by this corner. So each corner is a carbon, and the end here is given by this corner. So what we are saying is we can have C, H, H, H. We can have C here, H, H. We can have C here, H, H. C, H, 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 C. And then the end here we have H, H, H. But instead of having all those H, we remove them and just draw lines. The same thing here. This is a skeletal structure. This carbon here is this one. This second carbon is this one. This third carbon is this one. But now you see we have a junction. So this junction going up here is this one. So here we have another carbon. And then this carbon here is this junction. Oh, what did I do with the junctions? So let's see. 1, 2. Yeah, I think I made an error somewhere on the second, on this carbon. So let me just get rid of this. So how many? We have 1 carbon. Oh, okay. So we are starting from here. I flipped this one. So we are saying this carbon here is this. And then this second carbon is this. The third carbon, that's where we have a junction, is this. And this junction, which is going this way, is here. The fourth carbon, we have another junction here, is this. And then after that junction, we have this side of the carbon, and then we have this side of the carbon, which is this. So what we are saying is we can change, we can put C's and H on this one. So we know that the end H, the end C have 3H. This C has H. This C is connected to another C. So this one has one H, which has H. This C connected to another C, which has H, and H here. This C has H. So what we are saying is, if this is molecule B, this is molecule A. Molecule A and B are just the same molecules. Only that B is showing skeletal structure and A is showing a Lewis structure. So you need to be able to give me a skeletal structure if I give you a Lewis structure. And you need to be able to give me a Lewis structure if I give you a skeletal structure. So let's take note of that. Maybe before I go there, let me just show you how we do it. So I'll use this part because there is space. So for now, I'm not talking about naming. I'll talk about naming later for that one. But I'll just say, draw a Lewis structure of so this is a skeletal structure. I want to draw a Lewis structure for that. Now what I need to know is that this carbon here, the end carbon, so end line, this line here, this end is CH3. So which means we have CH3 here, CH3 here, CH3 here, and CH3 here. So every corner, like this one, is CH2, except a corner that has a junction. So a corner that has a junction, like this one, this type of corner will have C and a junction and then H and then continue. So we need to take note of that. Now, if I want to write a Lewis diagram for this, I'll start with this side and end with the other side. So this one is C, H, H, H. And then the second one here is C, H, H. The third one, this one, has a junction. So it would be C, H, and then we know that each line like this is CH3. So in the end there, C, H, H, H. And then we go to the middle one, C, H, H. That is this one. And we go to this one. It is C, H, and there's this junction here, C, H, H, H. And we go to the end one, which is C, H, H, H. So that's how you change from skeletal structure to Lewis structure. So let's take note of that. Yeah, let's hope you have already made that drawing. So I'm going to get rid of all this and then do the naming of branched chain alkanes part. Now, how do you name branched chain alkanes? Now, for that, let me show you the branches. So these are the branches. When naming the branched chain alkanes, you also have branches that you use. If you have a CH3 branch, like what we are showing here, this branch is known as methyl. If you have a branch with 2 carbon atoms, the branch is known as ethyl. So let's take note of the branches before we go to the action naming. So I'll continue with naming in the next video, but this is where we will start from.